the last talk of today, and we're happy to have Misha Gekhtman, who's going to tell us about twisted factorizations and multiple cluster structures on simple Lie groups.
Thank you very much. So first I want to repeat one of the main messages of Anya's talk and thank organizers for this opportunity. In particular, it's a great pleasure to give a Blackboard talk again. And apparently I still remember how to do it because I haven't even started and I'm already covered with chalk. I'm also happy to report that even though you heard Alec and Misha and I talk about this part over the years a few times, but a crucial part of what I'm going to talk about today was actually done right here at the Institute in September when we were all here. So I can rightly call this a work in progress, which also allows me to be vague when it suits me, right? But let me start with reminding everyone about cluster structures, what we'll call standard cluster structure on simple Lie groups. So this is due to Berenstein-Fomin-Zelevinsky. I'll just remind you basic features of those. So cluster structure on, well, more generally, double Bruhat cells in simple Lie groups. So there are quite a few nice features. So I'm not going to actually describe it in detail, but one thing which is important that there are plenty of clusters which are made of, well, in not A-type generalized minors, right? But when we're in A-type or when we're in Grassmannian, we can talk about minors and Fluker coordinates. This cluster structure is regular, which means that, well, initial seeds that you pick and all the cluster variables are regular functions on the corresponding group, and complete. And that means that either cluster algebra or more generally upper cluster algebra is naturally isomorphic to the ring of regular functions on your group G. So, well, I will call group G later. And then another nice feature, so this construction reflects nicely combinatorics of the corresponding while group. In particular, there is this nice construction using that uses factorization parameters, right? And then finally, which is important for me because I am contractually obligated to mention Poisson brackets in every talk that I give. It's compatible with what's called a standard Poisson Lie structure. And for now, let me just describe this as follows. So what does it mean to have a standard Poisson Lie structure on the group? And all my examples will be in the case of SLN or GLN, but they can be easily translated to other types. So if you consider just upper or lower triangular groups of 2 by 2 matrices, something like that, and equip it with a Poisson bracket of AB is equal to product of AB, and then embed it. So let's call it rho I. Embed it as a diagonal block. So there are I minus ones here, ones here, into your group GLN. So this map is Poisson. So this is one of the ways to describe, right? And the reason I want to do this because you will also recognize if you will have here this triangular block, or transpose of it, then this is also one of those elementary bidiagonal matrices which are used in factorization in the group of double Bruhat cells, or in parameterization, well, in theory of Lustig total positivity, and so on and so forth. Okay, so it's a very nice construction, and so we can consider an example. So I said it's our favorite seat, but I heard that, well, it's not everybody's favorite, but that's okay. And also, yeah, I forgot which side of the Atlantic I'm at, so our favorite seat. So this is a quiver which is made out of oriented triangles, right? We've seen it on Monday representing GUR for 8, but those are equivalent. And all we need to know now is what to put in these vertices. So, well, vertices are naturally numbered by, well, labeled by pairs of indices. So if I have here element in GLN, so I understand GLN is not simple, but this will not affect us at all. And then this initial seed made out of minors, as I promised, of the following form. You have Xij in the corner of this minor, and this is a maximal dense minor with this upper left corner, right? The maximal one that will fit into this matrix. Okay, and so as I said, this thing is regular, and that usually follows from short Fluke relation, or, you know, Jacobi, if you wish, your favorite identity for minors. It is complete, and this is because every matrix entry is a cluster variable in some of the clusters, right? We can just mutate it in such a way. So there is a regular procedure to do this. And well, okay, so compatible, as I said, with the Poisson-Lie bracket above. I will remind what Poisson-Lie means, but for now it's just, and this again can be proved rather easily because X can be, as I mentioned, kind of assembled from this little B2 plus minuses, and from that you can easily derive compatibility. And also it is well, let me just say also compatible, but just in a you know, colloquial sense, with the following map. So, well, again, natural map. If you have upper triangular and lower triangular matrices, and you multiply them, and you will end up in G in your group, right? So this picture contains actually cluster structures on this side and on this side, because all you have to do is just cut this in two and then reglue it, and through the process of amalgamation, you will get exactly the cluster structure you started. All right, but now I want to do something strange. So all of these properties are good, but this is not a unique regular complete cluster structure on this case GL4. So what I can do, for example, I can temporarily, or not temporarily, just simply unfreeze this thing, this variable, add some arrows. I have to be careful here, but yeah, so add some arrows. So there will be arrows that comes here, and another comes here, and then replace. So what was previously here was, well, this kind of function. In this case, this would be just an entry x for 1, but here I'll have to take x for 1 and replace it in a rather strange way with a minor x for 1, x for 2, and here I will put x 1, 3, x, 1, 4. It's not a minor because it's kind of twisted, but if I do that, I will still get a cluster structure on GLN, which is regular and which is complete. Okay? And this is not all. I can also do the following. So let me just repeat this procedure once more, but I need, where is it? I lost my, yeah. So I can now unfreeze this one. I can now add this arrow, and then I want to get the arrows correctly. So I'll get the one that goes over here, and then the one that goes all the way here. So I added another triangle. All right, so I deform the quiver, and now I will also replace something, but now I'll have to replace several things. So I had binaries sitting over here. I called them F12, F23, and F34. And what I'm going to replace them with is the following strange object. So it's, let me just draw it first. So I don't want to write down all the matrix entries, but I will just indicate. So this is a dense submatrix, so it will be clear what it is. And I immediately 1, 4, and here is x 4, 4, and then I add 3 zeros here, 3 zeros here, and then I put another block, and this is x 2, 3, sorry, x 3, 4. I cannot here x 4, 4 over here, and here I'll put x 4, 1. And this is, well, I'll just stop here, right? It's, again, contiguous block, right? So I have this strange composite matrix, and what I do, I will replace these functions, which were just normal regular minors, with minors in this matrix, which are not normal at all, but this is what's going to work. Okay, I probably, right. Yeah, I see why you look at me in puzzlement, because you normally consider minors of square matrices, and this was rectangular, and it's not going to be generalized that much. So, but yeah, like that. But the idea is clear, right? So this and again, it is complete a regular cluster structure, even though I did something strange to this quiver, right? And so, because you may ask, then, okay, if you do that, here you had also this compatibility with Poisson Lie bracket. So what about Poisson compatibility? And well, of course, we were going in the opposite direction. We always start with Poisson brackets first and derive the squares afterwards. So to answer this question, let me just remind you, so our modus operandi in general, so how do we construct cluster structures on various variety? So here's the philosophy. What you start with is some nice Poisson variety. And if you're lucky, you can find in this Poisson variety a regular, meaning made out of regular function, log canonical coordinate chart. And what that means is that you have a bunch of functions which are coordinates, and such that they're Poisson brackets, just their products times some constant with no summation. So the simplest possible thing that you can do, well, other than Darboux coordinates. And then from that, you can construct a seed which consists of this collection of functions fi and a quiver q, which is kind of a partial inverse of this matrix of coefficients Cij. Okay, and then so this gives you initial seed, and then again, under many well, circumstances, this will produce a regular crusty structure, and then you have to work hard to show this is actually complete. So there is, for both of my generalizations here, there is such a structure, and they belong to a very important class of examples. Which, well, consists of two actual examples here, Poisson-Lie groups. We have G and a bracket on G. And Poisson-Lie just means that if you take the multiplication map, this map is Poisson. And then related example as Poisson homogeneous spaces. And in this case, you have this variety with a bracket. And G is like here. And G acts on your variety. Okay. And the map G cross V, the action map now, action map is Poisson. Right, so those are examples. And so Poisson-Lie group, well, first example was given right here. And Poisson homogeneous spaces, again, this is one of the main examples in cluster theory. All the Grassmannians, cluster structure of Grassmannians comes equipped with this kind of structure. Right? And so now we'll consider sub-examples of this example because we deal with simple Lie groups. So the sub-example are Poisson-Lie structures that come from famous Belavin-Drinfeld classification. And so again, I'm not going to write formulas, but this is determined by the following data. So you start with what we'll call Belavin-Drinfeld data. And this contains two pieces of information. One is Belavin-Drinfeld triple. So what is that? So you have a map. I will explain what these are. So these things are subsets of simple positive roots. Gamma is a nilpotent isometry. All right, so roots live in the vector space, so this is an isometry, and nilpotent just means that if you keep applying this gamma, eventually you will get out of gamma 1. All right? And in addition, there is another piece of data which is, well, you have to mention. So the second piece of data is an element in the tensor product of the Cartan that satisfies some linear equation determined by gamma. Okay, so I'm not going to write it, but well, there are many solutions, and sometimes it's important to keep track of them. And so once you have that, what you construct is an element in the tensor product of the Lie algebra. This is Lie of G Z, so which is a solution, so-called classical Young-Baxter equation. Again, this equation I'm not going to write, but this is a constant operator that lives here. And from that, you can produce a Poisson bracket, which can be summarized in the following notation, which used to be called Leningrad notation, but now it's called St. Petersburg notation, right? That's just the fact. So, well, you have so in general you have square matrix. Square matrix, you need to write Poisson bracket between any two entries of those matrices. So this naturally belongs in a tensor product, right? And to comprise all these things, you can write a commutator of this element R with the tensor product of X with itself. So that gives you a Poisson Lie bracket on G. So we write it on generators, just expanded by Leibniz identity. And then more generally, you can take two sets of Belavin-Drinfeld data. Then you will construct these R matrices. One will be R left, and then other will be R right. And I apologize for this notation, but well, okay, it's clear what it means. And then we can also define a Poisson bracket that will depend on both of those things. By similar formula, you just do this thing. And it is no longer Poisson Lie, but it gives a Poisson homogeneous bracket with respect to the following action. So you have your group G, and then you have your group G, and then again you have your group G, right? And then it acts by multiplication on the left and on the right. And this one is equipped with bracket that comes from R left, and this comes equipped with bracket that comes from R right. Okay? All right, and so what can you do with all of that? Well, you can state a conjecture, right? You can state a conjecture, so this is what we did. So for any pair of Belavin-Drinfeld data, and please notice that I ignore this part. This part will not affect the conjecture, the R0 part. There exists a regular, complete, but possibly generalized cluster structure on G compatible with the corresponding Poisson bracket, which I will, so it will depend again on gamma L and gamma I. Okay, so in particular, examples that we have here on board, yeah, anyways, example above, we had 3 of them in the same picture. So first one was a standard one. So the first one corresponds to gamma L equals gamma R is just empty. There are no gammas, right? The second one was, let me just write, the pair was empty and gamma that sends √1 into √3. And then the third one was actually Poisson Lie bracket, where gamma left and gamma right coincide. Okay. So again, when I unfroze this one and change this function, I produced a cluster structure compatible with this kind of Poisson homogeneous bracket. And when I decided to unfreeze this one and change these 3 things, I produced cluster structure compatible with this Poisson Lie structure. And we have now the theorems that I can state. So this is the most general result towards this conjecture. So maybe I can state it in here. And that is that if G is GLN and gamma L gamma R is, I will explain what it means, so-called oriented aperiodic data or pair of data, then the conjecture is valid for cluster structures. You can drop generalized, right? So in this case, this conjecture is valid without generalized. So what does it mean to be, let me try to fit it in here. What does it mean to be oriented and aperiodic? So let's start with oriented. Well, it's A-type. And A-type, any subset of roots is made out of intervals. And because gamma is an isometry, then each interval will be mapped into interval of the same length. So we just make sure that it maps into that interval without switching the order, right? And then aperiodic is a little, so intervals, let me say preserved, okay? And aperiodic, it's a little stranger. What it means is the following. So I need a bit more space. So there is the following action on the set of positive roots. I can take the longest negative, the longest while group element, right? It acts on simple roots. Then I can apply my gamma left. And then I can apply again this thing. And then I can apply my gamma right. And it does something to each positive root, right? So this map has no cycles. That's what it is. Yeah, of course, initially wanted to call it a cyclic, but luckily we didn't do that because that would be horrible, right? Okay, so that's the theorem. And well, let me know. Theorem was a rather long proof even in this situation. And so let me now start with some, well, mostly self-criticisms regarding, so, well, I have no, well, shame about theorem itself, but about the constructions that we have. And so, first of all, the construction of initial structure, initial clusters is, or initial seed is very ad hoc. So, well, you kind of can see it here, or maybe here, right? So, well, initial variables are minors of this huge, generally speaking, block, you know, staircase matrices. All right, so we learn to love them, but if you try to explain how to construct them, this here goes your half an hour, and that's you're done. Yeah? Okay. So and so related criticisms, it is a lack of clearly theoretic meaning, right? Because in BFZ construction, you have generalized minors. Everything is very nice. You don't, yeah. You don't worry about if it's A-type or not. And then the main thing is compatibility with Poisson bracket, compatibility proof is, and I am justified to write it in capital letters, right? It's just horrible, right? Really. Well, so there is something good that came out of this because, well, for one thing, it is horrible, and we couldn't even compute any Poisson brackets in the group itself. We needed to compute brackets in a larger object in a so-called Drinfeld double of G, because we couldn't do it in G. But this actually led to some good things. So good things, let me just call them this. So this way, first of all, we discovered a construction of a generalized cluster structure in the standard Drinfeld double. So this is D of G is called, right? So which is good, and it contains actually the standard structure of Berenstein-Fomin-Zelevinsky as a substructure, and also generalized structure of the so-called dual standard Poisson group. And this was pushed further actually by my graduate student Dima Voloshin, who just not less than 2 weeks ago so extended to all cases covered by this theory. Okay. So that's good thing, but still you don't want to deal with such long proofs, right? Ugly computations. No one but, well, perhaps 3 of us, I'm not certain, and certainly Dima read this proof to the end. But what would be better would be to use some kind of factorization property, or maybe factorial properties, in a sense of this our matrices of the solutions of Yang-Baxter equations. So perhaps use factorization a la Berenstein-Fomin-Zelevinsky. And here, unfortunately, you cannot do this because, in general, these Poisson structures, they don't have this nice low-dimensional Poisson subgroups. All right, so that's no good. But at least, maybe, use the fact that if you have, or suppose I have, well, group with Poisson structure given by this data gamma gamma prime, and I have group with Poisson structure given with data gamma prime gamma 2 prime, and then it is well known and easy to check fact that if I do multiplication, then it will give me a Poisson map into G gamma gamma double prime. So for example, I can use empty data here and empty data here and glue the things together, right? But for that, you need kind of to have, again, this nice properties that I outlined here. It would be nice to have a Borel, another Borel, right? And glue them together, but also not Poisson-Lie submatrix, right? So what you would want is to have something like, I will write it B plus, and right here something like B minus, but we don't have them, right? So we need them. Okay, so because I wouldn't be talking to you if there were not a way around it. So let me actually try to tell where the idea came from. The hint was in the proof of the completeness part of the theorem. And I will do various sketches. So it contains the following construction. So I have my x in GLN equipped with this bracket corresponding to gamma left, gamma right. And from that, as we agreed, we can construct our favorite seed, right? So let's just, okay, right? And what is nice about the seed that it looks very much like the standard one, right? I just added something here. So am I off? Oh, sorry. Okay. Sorry. Should I stop right here? Yeah. All right. So, okay. And then okay. So there is a quasi-isomorphism that will send you into X, right? Just you restore then from the standard Q or something, right? And this will be in G standard, okay? So, and it turns out that this is actually, it's strange, but it is birational, and you can express it in just normal matrix terms. So maybe I can just quickly make a statement, right? Yeah. So here's the theorem then. So if you start with x and then you factor it as follows. So usual x minus x0 x plus factorization, but you start with something which corresponds to a lower nilpotent unipotent subgroup that is given by this root data, right? And then by the rest of the lower part, and then by the diagonal, and then by the entire upper part, right? So that this corresponds to reduced word. Okay? So you can always start reduced word with that. Okay? And then what you do, you define a new thing, which is obtained as following. You take gamma, this map, that you can extend to the nilpotent subgroup, and you apply it to the twist of L gamma 1, and then you take the inverse of that and multiply by x, right? So this is a map that you consider, and this map is Poisson with respect to here standard bracket. So it's this theoretic map. It is birational map. So what you can do now, here you have any of your clusters, my favorite seed, your favorite seed, any favorite seed. You can pull it back here, and this gives you your initial seed. And in particular, you can compute that exactly this way you will obtain when you consider the inverse of this map. This is exactly how you obtain this crazy matrices. But now I'm out of time. Right.
Any questions in the audience or in the chat?
Yeah.
I was just got a little bit lost when you did this yellow bit at the bottom and,
yeah,
and mutated at that vertex.
I didn't mutate.
Oh.
No, what I did. So the question was what happened to this vertex. So
this vertex is called 4-1, right? Not,
yeah, it
not
was yeah, it is 4-1. I didn't mutate. What I did, I made it unfrozen. I added some arrows, and I cannot keep 4-1 here any longer because this no longer will give me a regular structure. So I had to replace it with something else.
That's 1-1.
This is 4-1, and this is x41, x42, x13, x14. So it's not a minor. It's just
Sorry,
this.
what does that say?
Huh? It says that x41 that was
No, it
sitting
doesn't
here
say that.
before. Huh?
Yeah.
Yeah.
Oh, sorry.
Sorry. Yeah.
Okay. Thank you.
That's another beauty of Blackboard talks, right?
Okay. Well, that confused me a lot.
Yeah. Sorry about that.
The other question, suppose my favorite group was SLN instead of GLN. What do you do?
Oh, you just erase this guy. This is a determinant. Okay.
I
Yeah.
think Amy wants to be listening to that.
Yeah. Yeah. Yeah.
Okay, so then let's thank Misha again and all our speakers of today. And we will resume tomorrow.